Hey guys, welcome back to the demo lab. Today we're starting our first of a few different experiments looking at sound. Okay, so guys, I have all these cups set up, these fancy cups filled with water. All right, I'm gonna have you bang on these cups for me as we go throughout the experiment today. So do me a favor, and here's a pencil for each one of you. These are our fancy hidden sticks.
Or drumsticks.
That's right. Okay, so what we're gonna do is we're gonna kind of create different sounds and talk about why sounds change as the things that make those sounds change shape or for, in this case, fill. Okay, so take a look at the board over here with me. All right, so what we're thinking about here, sound is represented graphically through waves. We say that sound is waves traveling through a medium. And a lot of times we represent sound waves using what's called a sine wave.
Technically, that's a negative sine wave.
Is that a negative sine wave? Well, positive or negative sine wave, either way, it would have been positive if I'd started up and come down like this. So it can happen either way, and really the only thing I need
Sorry.
is, no, you're good, and actually, hopefully Becca will be sort of correcting me in terms of the math here as we go through. So, but a sine wave, we would call one cycle of a sine wave the distance from where the negative sine wave in this case begins to where it ends. This would be considered one cycle. Okay, and in music, we often talk about hertz. Hertz are a way we represent cycles in terms of sound. So what we say is the time that it takes one cycle to pass a point, or really if a one cycle passes a point in 1 second, that's 1 hertz.
In math, that's called the period.
And it's called a period in math, and actually in a lot of science classes as well.
Yeah.
Right. So, but in music, we would relate it to hertz, and we would essentially say, okay, so if you have one cycle pass a point in 1 second, that's 1 hertz. If 2 cycles pass in 1 second, that would be 2 hertz. Okay.
Okay.
And the lower the hertz, the lower.
That's frequency, though, right?
It's related to frequency. It's absolutely related to frequency. So let's look over here at our frequency picture, right? So here I have 2 different waves represented. One wave is low frequency and one wave is high frequency. So low frequency is directly related to low hertz. In a sense, they're the same thing. We're basically saying how frequently does a full cycle pass a given point. So if we said, if this is the given point, and this wave, now one thing we have to imagine is sound travels at the same speed, even if it's high frequency or low frequency. And that speed is 1,126 feet per second. That's the speed of sound under normal environmental conditions. So my low frequency wave and my high frequency wave are traveling at the same speed, but how quickly they're passing a given point, like if my pencil was that point, my low frequency wave, fewer cycles will pass in the same time as my high frequency wave. Does that make some sense?
Yeah.
Yeah. Okay. So low frequency is directly related to low pitch, a low sound. High frequency is going to be related to a higher sound. Okay, and there's a direct relationship there, which is kind of useful and convenient. So let's switch back over here to the demo lab area, and let's just talk a little bit about how frequency changes. So, Becca, how would you describe the water level on the cup nearest you?
It's a high level.
Sure,
of
and
water.
then Lily in the middle. The levels are high, low.
Semi-middle, like length, yeah.
Yeah, somewhere in the middle, and then Nate looking at that green glass there.
That looks low.
Okay, so let's do this. Becca, will you tap the side of your glass?
Here, I'll do this side.
Nice, and honestly, the low frequency sounds are a little bit less sharp, but excellent. Lily, will you tap the red glass? Okay, what's the difference in those sounds?
Much higher than the filled glass.
Absolutely, that's higher pitch. So we've got low pitch, higher pitch. Nate, why don't you go ahead and tap your green one? Excellent. Okay, so what we can see is, or maybe you guys could tell me, what's happening to the frequency of the sound as the water level decreases?
It's going
Getting
up.
higher.
Yeah, the
Higher
frequency is increasing. Okay, now this actually sort of blew my mind. I was expecting it to be the opposite. Okay, so look at this. I've got something to show you guys here. So this is a soda pop bottle. Right? Have you guys ever made music by blowing across the tops of a bottle?
I have, yeah.
Would you describe that as a relatively high or low sound?
Low.
It's kind of a lower sound, right? So I'm going to pour some water in here, change the water level, and let's see how the sound changes. All right, so tell me now, higher or lower frequency or pitch?
Higher.
Higher, right?
Yeah.
So I expected, because I knew that that was the case, as the water level increases in a bottle that you might be blowing across, you're going to end up with a higher frequency sound. But interestingly, it's the opposite, at least with these glasses. Okay? So as the water level increases, we're getting a lower frequency. As it decreases, we're getting a higher frequency. Also, I just have to say I had to cheat here a little bit. I only had 5 glasses of the same size. So you'll notice that the yellow level here is higher than the green level here. What would you expect, given what we said, what would you expect the difference between these two to be?
Expect this to be lower.
Right, but it turns out that the size of the glass actually has a big effect. So Nate, do me a favor, play the green and yellow glasses. So because this glass is smaller, we're actually getting a higher frequency. And now I've got 2 even smaller glasses. Nate, go ahead and play those last 2 for us. There we go. So by changing the size of the glass, we can absolutely change how the frequency is going to be produced. So I had to sort of play with this to get what is a full scale. So let's see if we can do this. I'm going to see if we can play all the notes across. Okay. Now we're going what's called an octave. So in Western music, we have these things called scales. Scales typically have 7 unique notes. And then the 8th note is the same note as the first note, just 1 octave, we say, higher. So we'll do this. Becca, will you play the blue glasses? Lily, will you play the red and orange? And green, let's say, and then you can finish it out.
Okay.
Okay, so we'll play in that order, starting with Becca.
All right, ready?
Ready. Beautiful, right? Not so bad. So this is a really easy thing to do if you wanted to set this up at home. You just need glasses, ideally all of the same size, although you can see that you can sort of cheat. And it took me a while of filling the glasses and emptying them to get them at the right levels.
So the shape doesn't matter, like you didn't choose this shape for any particular reason.
Not necessarily, and actually ideally I would have just chosen simple wine glasses, but this was what was available to me. But the shape just shouldn't matter as much. Glass rings pretty well, right? So let's just sort of, we're going to relate this back to some other things and just talk about how frequency changes, and then we're going to add in this thing called amplitude, okay? So I'm going to hand out 2 ukuleles. I think I'll do, here, I'll give one to Becca. Here.
Thank
I'll
you.
give one to Lily.
This is guitar size for
Nate,
me.
I'm sorry I don't have a uke for you, but I figured I just wanted to give your arms a rest for one.
Yeah, it's been a few hard weeks.
Nice. Okay, so let's hold the ukuleles the same way. And ladies, I want you to play the string that's closest to your face. We'll go Becca first, now Lily. Oh, can you, sorry, don't
this
press
is
anywhere.
No
Oh,
frets.
no.
Just play the open.
Okay.
Okay, so if those are in tune, they should be relatively the same notes. Is one higher or lower than the other?
Say it again.
Do we have a higher pitch or a lower pitch between those two? Let's do Becca first. Lily?
It's about the same.
It's
pitch.
really about the
Yeah.
same pitch, right? The sounds are slightly different.
Yeah.
Okay, so if we can jump back to the board for 1 second here. So once we get back to the board, which should only take a minute, anytime now screen. Well, if you guys are looking here, you can see my simple sine wave. Okay, so now in reality, nature does not produce sounds as just a single simple sine wave. We can do this electronically. We can make electronic sounds that are perfect single sine waves. But when we're making real sounds out of a ukulele, or when we hear something like a dog barking, or any kind of a sound out there in the real world, we're not just hearing a single sine wave, we're hearing many, many sine waves together. And so when we think about these 2 ukuleles, each of those ukuleles has a different body size, and just slightly. This is called a tenor uke that Becca has, and then this is a soprano uke that Lily has, so different body sizes. And that's really going to change ultimately the timbre, we call it, the tone of the sound. And you can get much larger ukuleles than that even and change the sound further. But what do you guys notice? Compare the length of your strings.
My strings are longer.
Your strings are longer? So what we should get there, we should have a slightly lower sound from that, okay? So do me a favor, we'll just do one last little thing with the ukulele. Becca, can you play an open string for me? Any open string? Okay, so relatively low sound. Becca, pinch that same string up a few frets and make the sound again.
Oh.
It's beautiful. You're well on your way to being a virtuoso. Nate, could you tell me, when Becca shortened the string by pushing in the fret, what happened to the frequency?
Can you do it again?
Sure. So here's open. Here's
It's a higher pitch.
Yeah, absolutely.
Higher frequency.
Higher frequency, absolutely. So that's right. So the shorter the string is on a stringed instrument, we get a higher frequency or a higher pitch. Okay, I just want to do one last thing. If you guys would just set those ukuleles down there behind you. Okay, I'll take that one for you, Becca. Thank you. Okay, so the last thing we're going to do is just talk a little bit about this idea of how things work together. So we have some sounds that work really well together and some sounds that don't as well. So different sine waves combine pretty perfectly. In a scale, if we take the first, the third, and the fifth, we would get what's called a chord. So what I want you guys to do is each play those, but I want you to do it in unison. So I'm going to count down from 3. I'll go 3, 2, 1, and then have you hit, okay? So here we go. 3, 2, 1. Beautiful. That's a chord. I don't know what chord because I'm not quite sure what that root note is, but that would be a major chord right there. All right, now let's hit this one. I'll have you guys do blue, orange, yellow. Okay, get ready. 3, 2, 1. So that is a minor chord. Okay, and what we get here is different sine waves combine together in a way to make either major chords we have in Western music or minor chords. Major chords are often called happy chords, minor chords often sad chords, but they're harmonies in either case. Okay, so now what I'll have you guys do is play 3 notes right next to each other and see what happens. So green, orange, red, line up to do those, and we'll count it down. 3, 2, 1.
Oh,
All right, hold on, let me try again. Get ready.
I missed.
3, 2, 1. That one has more of a clashing sound, and so we would call this dissonance, right, when the sine waves are not lining up as happily. Okay, and if you're interested in seeing how this stuff works, I strongly recommend.
On a graph.
So it looks really complicated. Honestly,
Okay.
even harmonies, even things that you would think, oh, they match up so perfectly, even those can be really messy. And a single note coming from that glass is actually many, many sine waves. There's one sine wave that we hear that's the main note we hear, but there are many overtones and undertones that come with it. So looking at these things on a graph, it's very simple to look at just the single sine wave, think about the single note. But when we get real sounds in the real world, they're very complex mixtures of sine waves. Cool, I hope you guys enjoyed this experiment. I really hope you try it at home. This is very easy to do. Food coloring is readily available, so you can make a pretty glass scale like we did. And thank you guys so much for tuning in. We will see you back in the homework hotline studio in a few minutes.